In the vast expanse of the universe, an unexpected discovery is quietly rewriting our understanding of cosmic laws. The Andromeda Galaxy, long regarded as the Milky Way's neighboring twin, has now presented an enigma that challenges our fundamental assumptions about the cosmos. Recent astronomical observations have revealed a stunning asymmetry in the distribution of Andromeda's satellite galaxies, a finding that defies the predictions of existing cosmological models. This anomaly has sent shockwaves through the global scientific community, potentially forcing us to re-evaluate decades of research on cosmic structure and evolution. Traditionally, large galaxies like the Milky Way and Andromeda are accompanied by numerous dwarf satellite galaxies, remnants of countless galactic mergers and disruptions throughout cosmic history. These satellites are seen as integral parts of the gravitational narrative that has shaped the universe over billions of years. According to the standard lambda cold dark matter CDM model, the cornerstone of modern cosmology, the formation and distribution of satellite galaxies are considered a result of random, chaotic processes. In theory, these satellites should orbit their host galaxies in a roughly uniform, isotropic manner, like celestial bodies floating aimlessly in a gravitational pool. However, the Andromeda Galaxy has broken this mold in a most dramatic fashion. Detailed observations show that over 80% of its 37 known satellite galaxies are concentrated within a narrow 107-degree arc of the sky, predominantly on the side facing the Milky Way. In other words, instead of a 360-degree distribution, Andromeda's satellites cluster within just 64% of the available space. Such a phenomenon occurs in less than 0.3% of the hundreds of rigorous cosmological simulations conducted so far. This is no mere observational error or statistical fluke. As astronomers discover more faint and distant dwarf galaxies, the asymmetry only becomes more pronounced. A research team from the Leibniz Institute for Astrophysics, Potsdam, published this groundbreaking finding in Nature Astronomy. Through meticulous data modeling and orbital analysis, they confirmed that the extreme distribution of Andromeda's satellites lies far beyond the explanatory power of current cosmological theories. The Andromeda Galaxy isn't just presenting an unusual cosmic map. It's challenging the very foundation of our scientific understanding. Scientists have found that this asymmetry isn't an isolated anomaly. With the advancement of observational technology and the inclusion of more and more faint dwarf galaxies in the dataset, the skewed pattern persists and even intensifies. Kazuo Jimmy Candace, the lead scientist at the Potsdam Institute, emphasized, even in the deepest observations, this asymmetry remains consistent, unaffected by sample expansion or improved distance measurements. This indicates that we're dealing with a real cosmic phenomenon, not an error or coincidence. To validate these findings, the team conducted extensive numerical experiments. They simulated hundreds of galaxy systems with different initial conditions within the CDM framework, hoping to find a similar asymmetric distribution. The results were astonishing. Only about 0.3% of the simulations produced such extreme clustering akin to rolling the same number 6 times in a row on a fair die. This suggests that, even accounting for observational uncertainties, galactic mergers, and variations in initial conditions, the current cosmological model struggles to explain the extreme nature of Andromeda's satellite system. In essence, Andromeda is challenging the universality of our standard cosmic paradigm. But the mystery doesn't end there. The Andromeda Galaxy harbors another equally perplexing feature, pushing the boundaries of our knowledge even further. Alongside the asymmetric distribution, roughly half of its satellite galaxies orbit within an incredibly thin, coherent plane, moving in an orderly fashion reminiscent of planets orbiting the Sun. Such planar structures are extremely rare in the universe. According to CDM-based simulations, the formation of such a thin, dense, and dynamically stable satellite plane is highly improbable, if not impossible under normal circumstances. Thus, we're confronted with a double anomaly, an asymmetric distribution of satellites combined with their alignment in a stable, rotating plane. If we uphold the current cosmic model, this dual anomaly strains credibility, threatening to undermine the entire theoretical framework. The Andromeda Galaxy has become a living cosmic paradox, a celestial system that, according to existing models, should not exist in its current form. To appreciate the gravity of this challenge, we must revisit the core tenets of the CDM model. lambda represents dark energy, the mysterious force driving the universe's accelerated expansion, while CDM stands for cold dark matter, the invisible scaffolding that shapes large-scale cosmic structures. Together, these concepts form the basis of our current understanding of the universe's origin and evolution. On a grand scale, the CDM model has been remarkably successful, explaining phenomena such as the cosmic microwave background radiation and the distribution of galaxy clusters. However, when we zoom into the scale of the Milky Way and its neighbors, cracks begin to appear. The Andromeda satellite system stands as one of the most striking and persistent anomalies. According to the CDM model, satellite galaxies should form through a chaotic, random process, arriving from all directions and eventually settling into a roughly spherical distribution around their host galaxy. While the occasional satellite plane or slightly asymmetric distribution isn't entirely impossible, such phenomena are extremely rare in simulations and typically transient and unstable. Yet in the Andromeda galaxy, we observe a long-lasting, ultra-thin satellite plane with a distinct rotational direction, coupled with a severely skewed distribution of satellite galaxies. This combination of features isn't just statistically improbable. It's virtually non-existent in the most advanced cosmological simulations today, such as the Millennium, Eutrope, or EGEO projects. This forces us to confront a fundamental question: is the Andromeda galaxy merely one of the universe's many oddities, or does our understanding of cosmic mechanics contain significant, undiscovered gaps? The scientific community has proposed several hypotheses to explain this enigma. One theory suggests that satellite galaxies don't cluster randomly but align along the cosmic web's filaments, the large-scale structure of the universe. In this scenario, gravitational forces along these cosmic filaments guide dwarf galaxies towards Andromeda in a specific direction, creating the observed asymmetry and planar structure. However, maintaining such an initial arrangement over billions of years, resisting gravitational perturbations, galactic mergers, and environmental noise, remains difficult to explain convincingly within most current models. Another hypothesis focuses on the Milky Way. Some propose that gravitational interactions between the Milky Way and Andromeda in the past reshaped the spatial distribution of Andromeda's satellites. But current data analysis indicates that the Milky Way's gravitational influence isn't strong or sustained enough to fully account for the highly ordered and coordinated nature of Andromeda's satellite system. So, where does the problem lie? Are there unknown forms of interaction we haven't considered? Is the nature of cold dark matter more complex and dynamic than assumed in the CDM framework? Or could baryonic physical processes, like energy feedback from supernovae or interstellar storms, play a more significant role in shaping small-scale galaxy distributions? These questions go far beyond simple model adjustments. If the characteristics of Andromeda's satellite system are further confirmed, they could trigger a complete overhaul of our current small-scale galaxy formation theories and even reshape our fundamental understanding of dark matter's dynamics in the local universe. Thankfully, this story doesn't end in confusion. Instead, it has opened the door to a new era of exploration. The Andromeda galaxy is becoming a natural laboratory for understanding the universe's deep-seated structure, an unprecedented cosmic test. Scientists have quickly sprung into action, developing more advanced and detailed cosmic simulations. They're incorporating complex physical factors previously overlooked, from the dynamic evolution of satellite populations as they fall into host galaxies to the profound impact of neutron feedback on galactic environments and the subtle, chaotic structural changes within dark matter. A key player in this global scientific race is the Euclid mission, launched by the European Space Agency in 2023. The Euclid telescope aims to map the geometric structure of the universe's dark side with unprecedented precision, revealing how dark matter and dark energy have been distributed and evolved throughout cosmic history. With its ability to create 3D images of billions of distant galaxies, the Euclid mission will allow astronomers to systematically investigate whether Andromeda's satellite system anomaly is an isolated case or if there are more hidden galaxies in the universe exhibiting similar asymmetric and planar structures. If Andromeda isn't unique, Our standard model of the universe's origin and evolution may be more fragile and limited than we thought. Meanwhile, ground-based observatories are also in full swing. Research teams are using large telescope arrays to collect detailed kinematic data on Andromeda's satellite galaxies, measuring their velocities, orbital trajectories, and dynamic evolution. Through this data, scientists hope to trace back in time and reconstruct the complete history of these satellites. Were they formed around Andromeda under its gravitational influence, or captured from neighboring galaxies in the early universe? Did they fall in individually, in groups, or are we witnessing the final echoes of an ancient galactic collision? Scientists are also expanding their scope, examining the local group of galaxies, which includes the Milky Way, Andromeda, and a series of neighboring galaxies. They aim to find similar anomalies on a larger scale and build a vast sample library of satellite systems for more statistically significant comparative studies. In the coming years, missions like the Sloan Digital Sky Survey SDSS, the Dark Energy Survey, and the upcoming Nancy Grace Roman Space Telescope will provide a continuous stream of new, high-precision observational data, enabling astronomers to create a more comprehensive map of satellite galaxy systems. All these efforts lead to a profound question: is the Andromeda Galaxy a solitary cosmic oddity, or is the universe, which we thought we understood, actually more mysterious than we're willing to admit? Bathed in the cold light of the stars, we once believed that understanding the universe was only a matter of time. But Andromeda quietly reminds us that even the most perfect models are just fragments of the cosmic puzzle. Perhaps we've never truly grasped the whole picture, and the unknown always outweighs the known. In this endless journey, science isn't a destination, but a guiding light, illuminating our path through the darkness and urging us to keep exploring. The questions never end, and the answers always lie just a bit further ahead. Thank you for watching.